In this episode about the physics seminar at Stanford, Optical Quantum Physics, I want to talk about precision and atomic clocks in particular. There's a series of presentations that went into the problem of precision, whether it's time or whether it's other areas of the design space, such as position, angular momentum. I think the problem is the same. And the fundamental problem in atomic precision measurement is that you have atoms interact with light and you measure the frequency that the light requires to move the atom from one energy state in another. This is obviously very crude, but in a nutshell, that's the problem that is the technique by which precision can be measured. So you have the precision in terms of how many frequencies is required to move a cesium atom from energy state T1 to energy state T2. And if that differs, so if that frequency is different, we can then infer from that particular situation that could be due to maybe dark matter. It could be due to different gravitational fields of the Earth. It could be due to maybe relativistic issues that, if we measure something in a different gravitational field, then maybe time has a different value versus if we measure it, at sea level or versus on Mount Everest, or if we measure something in the ISS. So those are the kinds of things that caught my attention. In particular, I'm going to put all the links in the show notes so I don't spend my time here with names and details and the mispronounced people and things like that. But there was a gentleman from Berkeley. He spoke about precise measurements of time using a specific technology with atomic clocks that uses several atoms. So you have, think of it like this. You have a lattice with lasers, you trap atoms in there, and then you fire lasers to those atoms in parallel, and you measure their energy states, and then you can have deltas that are due to errors, and you can cancel them out. So having multi-atom atomic clocks just makes things a little bit more precise. Another gentleman that looked at gyroscopes and particularly measuring angular momentum and rotation of an object by using an atom. And again, the idea is to be more precise, and the way you can achieve that is by first trapping the atom in a cavity, so having it behave exactly the way you want before you even start transforming it. So the problem set here is multifold, right? On the one hand, you're trying to isolate the system as much as you can to the point where when you do a transformation, you are certain that you're inducing the transformation and the subsequent new type of behavior of the system based on your desired transformation and not other noise. So this is the key. What I thought was more interesting also here is the actual use case for precise time. That's really an interesting, almost philosophical question. And I want to talk about this a little bit more. This is not even on podcast. It's September 27, 2024. This is Krim Delco. For the day, the fund is up 2.5%. The market is down 20 basis points. For the year, we are up 25.2%. The market's up 20.2%. We're outperforming by 5%. So why do we need highly, highly precise atomic clocks? And there's a paper by the Berkeley professor, also link in the show notes, that's really describes that really nicely. So that's why I want to talk about this a little bit more. So why do we need precise time? Well, one is we can calibrate cosmological constants. So in other words, a lot of our theory, let's say the most up-to-date theory as far as cosmological behavior and astrophysical behavior is concerned is all being described with general relativity. But general relativity does assume cosmological constants. And with more precision, we can have better results in the theory. And particularly when we talk about, for example, dark matter, we could say that we are detecting dark matter because general relativity would predict different results than the ones we see. And our conclusion is, well, there must be something else. But there is also the potential that maybe our cosmological constants are not precise enough, and that if we add precision, we also reduce the amount of unknown matter in the world. So in other words, this is, really, kind of Heisenbergian, actually inverse Heisenbergian, where you increase the precision in one area and that gives you more precision in another area. So if we have more precise cosmological constants, we could actually have a better result in general relativity when it comes to measurements such as, for example, the rotation of stars and things along those lines. So that's one of the applications of highly precise clocks. So again, just to be clear, the problem that was discussed in the seminar was how can we get more precise clocks? And the physics of that, for example, having multi-atoms in a lattice being manipulated, that is, the idea there is statistical inference, having reduced errors and things like that. But the question I'm discussing here is, why do we even need more precise clocks? And one is, of course, calibrate cosmological constants, detect dark matter. So let's assume we have dark matter. Let's assume it's out there. If we have a more precise measurement of time, we can then also have a more precise measurement of dark matter. In other words, if we have, let's say, atom X, which is being measured in an atomic clock here, let's say in situation Y, and then situation Z, and atom X has a different measurement of atomic clock time, such as, for example, a second is more or less than the 9 million, gigahertz or whatever it is, or 9 million hertz, or it doesn't matter. I think it's 9 gigahertz per second or something like that. Well, anyway, the point here is, of course, that we could have differences in the behavior of the atomic clock could then give us insight into the existence of, for example, dark matter, but it could also give us insight into relative geodesy. I hope I right. So geodesy is the study of the Earth's gravity and the Earth's position and the Earth, sort of some of the Earth constants that we use to study the Earth. And the more precise measurement of time can help us in that field, because we could have, for example, different gravitational fields being detected by the clocks, whether we measure them at sea level or whether we measure them on Mount Everest. The same precision conversation also applies to, for example, gyroscopes. What do we do there? We try to measure the movement of a body without having an external system, and the way we do this is with angular momentum and rotation. And again, more precision gives us better insights into how the body moves. It gives us relativistic insight. And of course, the application there would be something like when we go to Mars, we need those types of precisions, because here we have the proverbial problem of launching an arrow from here and we want to hit Mars. And if we are off a little bit, even if it's 10 points behind the comma in some of the cosmological constants, we could run the risk of totally missing the target. So to summarize, this seminar really was very insightful. Okay, I would say there's a couple of things I want to say. Number one, I think the interaction between light and matter is at the heart of physics today. Whether we call it quantum physics, optical quantum physics, I just call it physics, because it's really the most interesting part, in my opinion, of physics. More precision gives us, on the one hand, better explanations, but it also gives us potentially explanations that we might, so for example, we might think that general relativity is wrong, but it could be actually right. And what we don't have is a precise measurement of time and and cosmological constants. So this whole conversation about dark matter and dark energy could be really a conversation about, hey, do we actually have enough precision to measure, to use general relativity to actually do measurements? I think lastly, what I want to say is, again, this quest for precision sometimes could come across maybe as a little bit of a sort of l'art pour l'art type situation. But in my opinion, it is much, much more than that, because it really helps us understand what, let's say, general relativity is all about. It helps us understand what we mean when we say dark matter. In general, it helps us to understand what it means when there's something we don't see, but it's there. Well, maybe it's because we don't have the right analytical tools. And it starts with, the precise measurement of time. Time is an important concept in physics because every kind of transformation is driven by time. So the more precise measurement of time we have, the better we can measure transformations and the better we can explain theories such as general relativity. Thank you.